Oh, thank you very much. And thanks for this opportunity. It's really a great honor for me to give this talk. I only regret that I'm not able to be there physically, but my mind is very much amidst friends and family remembering Vishu. I would like to tell you today about some of the personal encounters. This is really not a technical talk, but more recalling Vishu's influence on me and my research, and how he has shaped my way of thinking, not only about the research, but also about life. If we can go on to the second slide. My first interaction with Vishu began what is now almost 40 years ago, only a few months. I was studying in the National College for my BSc, and at that time, Narasimhaya had established called Bengaluru Science Forum. I think it was established in '69, and it conducted a science festival each year during the month of July. It used to have science talks, but it was in the month of July that we had a bonanza of talks on various issues, including talks by neurosurgeons, on botany, and about films and all sorts of things. And it was one of those occasions that I heard Vishu deliver a lecture at the forum during the 1977 Science Festival. Undoubtedly, it was the most fascinating physics lecture I had heard. The entrance to National College in Basavanagudi, Bengaluru. If you go inside, there is an open air theater. But if you follow to the right, then you come to a quadrangle, which is what was called the closed theater. And the lecture that I heard, I very vividly remember, it was on the first floor, on the room in the lecture hall that I'm indicating by the arrow. It was full of humor but he had a very serious disposition. Those of you who have met him and heard him know that he doesn't even give you an inkling that he is, making jokes or anything like that. So it was not clear whether we were supposed to laugh. It was a time when I was thinking whether to continue my passion for music. I was learning at that time music on Veena. And I thought that that's what probably was going to be my career. But I was fascinated by physics too. And I was slightly struggling between physics and music, but was inclined more towards music, at least until I heard Vishu. And Vishu's lecture was undoubtedly the turning point. And it all not only focused my mind, but also general relativity. And it was that Vishu's lecture and very little known book by Landau, The Meaning of Relativity, are the two that influenced my career. But it was these personal encounter with Vishu was really extremely fascinating. Fast forward 4 years, next slide. I joined Indian Institute of Science after completing my Masters of Science in IIT Madras. And I wanted to work in general relativity. I mean, throughout my MSc, I really was looking forward to learning relativity, but there was nobody in IIT Madras that taught relativity. At that time, some of you may know Balakrishnan, V. Balakrishnan, he joined IIT Madras, and he, for the first time, organized as a part of our curriculum. I was extremely interested in doing that, and I chose as my topic compact objects, which included neutron stars and black holes. I presented that seminar, and that's one of the best things that I did during my MSc, enjoyed really greatly. But there was nobody to teach general relativity at IIT Madras, so it had to be something that I had to learn myself. Lots of trial and error. But at the end of it, Balki actually called me to his office one day and asked me what I wanted to do. And I told him I wanted to do research in general relativity. He said, well, I think there is a professor who has come back, or is going to come back soon. No, I think he had already come back. I'm sorry. He'd already given the lecture at National College by now. This is 1981. And he suggested that I should go and work with him. And in fact, I recalled to Balki and told him that would be fantastic. But I didn't know how to apply to Raman Research Institute. I got this PhD position in Indian Institute of Science. I joined there. And I mentioned to one of the staff members there that I wanted to work with Vishu, because there was really nobody else who worked in classical general relativity. There were a couple of people who knew general relativity, such as RR and Mukunda, but they were not working in general relativity. I had mentioned this to one of the staff members, but somehow the news reached the head of the department, which was Vishveshwara at that time, and he called me to his chambers. And he said, if I wanted to work with anybody outside in the Indian Institute of Science, I should give up my position and leave the institute. And that was a massive missed opportunity. It was just a neighboring institute, and somehow the administration was not was not sympathetic to the research that I wanted to do, and insisted I must join somebody in Indian Institute of Science, Bengaluru. So I couldn't work with Vishu, but I saw him from a distance. I think many of us used to frequently go to Raman Research Institute for seminars, and he kind of became Drona, from whom I learned from a distance. And that continued, and we had interactions, and I came to know over the years that he's a very likable person. He had absolutely no sort of air around him. He treated everyone with respect and made us welcome to his chamber and talk to him at any time, whatever we wanted. This is something that I adapted later in my life. I missed that opportunity, but I made sure that my students and postdocs had the complete freedom to work with anybody they wanted. And almost every one of my students has worked with at least, apart from me, during their PhD. With postdocs, it's even more common. And I think that sense of sharing scientific ideas is what I, as an ekalavya from a Drona. So moving on to next slide. You have seen this cartoon. This is the cartoon of the program. It was 60th birthday, and it was a massive honor for me when Bala Iyer and Biplab Bawal asked me to contribute an article to this fantastic volume, which was supposed to be in honor of Vishu and to be given to him on his birthday, soon after. But the interesting thing here was that he had absolutely no idea this was going to happen. I just very vividly remember this was during the ICGC. He was secretly called to Ajit Kempavi's house, where everything was hush-hush. And when the book was presented to him, he was absolutely thrilled. And it was during, it was for this article that I wrote in honor of his 60th birthday that I made a promise. It was kind of foolish looking back, because it might have been that I couldn't have fulfilled that promise. And I told him that I hope that one day I'll be able to come and tell you that we have detected the quasi-normal modes that you discovered. And that's the promise I made. And that was kind of my Gurudakshina. If you move on to the next slide, on February 11th, on the day of the announcement, I wrote to Vishu, "Dear Vishu, I had promised nearly 20 years ago that one day I will come and tell you that we have detected those dying tones of black holes. Well, now we have done it. Here is a link to the discovery paper and a paper in which we have looked at the quasi-normal mode. Congratulations." In the best of his spirits, Vishu wrote back to me a few days later, "Thank you immensely, but your promise was that you would come and tell you that we have detected or seen these black holes. So you have to come down to Bengaluru to keep your promise. So don't forget to bring a few bottles of Cardiff champagne so we can celebrate the black hole RINGDOWN together." And he goes on to say a few more things. But it looks like, I don't know whether he read the paper on quasi-normal modes or not. He concludes by saying, "I only got the discovery paper to be another quasi-normal mode paper." I hope somebody gave him that paper. I actually sent another mail giving him a link to the actual paper where quasi-normal modes were discovered. So what was it? What was this Gurudakshina? Moving on to the next slide. This is the discovery paper. It starts off with some description of when gravitational waves was discovered by Einstein and black hole solutions of Schwarzschild. Next slide. And right in the second paragraph of this paper, it reads, "Also in 1916, Schwarzschild discovered or published a solution for the field equations that was later understood to describe a black hole. And in 1963, Kerr generalized the solution to rotating black holes. Starting in the 1970s, theoretical work led to the understanding of black hole quasi-normal modes." And there are three papers cited, 8 to 10. If we go to the next slide, we see that number 8 is that of C.V. Vishveshwara in the Nature journal, published in 1970. That was the first ever paper on understanding how black holes react to an external perturbation. The other two are to William Press and Chandrasekhar and Detweiler, and these are three seminal works which started the black hole perturbation theory, but very clearly the honor for the seminal paper goes to Vishu. On to next slide, slide 9. He is truly the Quasimodo of black holes. Without any doubt, first to hear the sound of a black hole. After the gravitational waves, I read quite a lot in Indian newspapers as a black hole man of India. But he's not just black hole man of India. He showed the world how to listen to whispers of a black hole or of the space-time warpage itself. I think this is a fundamental work of extremely high significance. And I'm really very proud that it is this person who influenced my own career, and to have met him and shared some of my life with him. So over the next about 20 minutes, I would like to share with you the technical side of these things, and I hope it's not over the board. Let's start with slide 10 that shows the graphical representation of the top two panels there show you the raw data. It's almost raw data. There's not much signal processing that is done. Two LIGO detectors. The left-hand trace is from Hanford. The right-hand one is from Livingston. But on top of that, it shows the Hanford trace as well. And what you see is a chirping signal characteristic of two black holes or two neutron stars coming together. But what is important here is how this system ends its life. Towards the end, the signal, which was ramping up 200 milliseconds, all of a sudden completely dies out. And that is what is characteristic of a black hole. And this is the reason why we all got excited. Going on to the next slides, black holes are quite, ubiquitous. On slide 12, I show how we know that the center of our own galaxy, it looks like you guys didn't play the keynote because that had a video, but it doesn't matter, don't worry. The black hole at the galactic center is demonstrably shown to contain an object which is about 4 million solar masses, a little more than 4 million, but it's an object which is not directly seen, but we do see orbits of stars around it. And because of that, we know that there is an extremely compact and dark object. And the current explanation for that is that it is a black hole. It's a very heavy black hole. And it is supporting the entire galaxy. But there is no direct evidence that we have seen black holes. Not only that, going on to the next slide, X-ray astronomy has, for many, many years, detected black hole candidates. What you see in purple here is just a visual demonstration. X-axis has no meaning. On Y-axis, it shows the masses of black hole candidates. And the black hole candidates that X-ray have tried to demonstrate that these are nothing but black holes, but that has really not happened so far. It is again an indirect evidence, and the best possible explanation for them are that they are black holes. But how do we then know that the black holes or objects that LIGO has detected are really black holes and others are black hole candidates? Why do we say that? Let me walk you through the argument here. On the next slide, I just say listening to black holes. And how do we listen to black holes, which is what we should thought. And today we understand this in the following way. Moving on to slide 15. Have the unique property that even though they are macroscopic objects, they are characterized by only two numbers: their mass and their spin magnitude or rotation. Now, a black hole sitting out there doesn't do anything. You can't detect it by any means because it doesn't emit any electromagnetic radiation or light. However, if you perturb a black hole by some method, by scattering gravitational waves or light rays from it, as Vishu was trying to do, then it does emit characteristic modes of oscillations. These are oscillations of the space-time itself. The black hole is a space-time warpage. This warpage, what comes out is the space-time warpage. The emitted modes are what we call complex frequencies. These have a negative imaginary part. I gave you some examples of normal mode frequencies could be slide 16, positive that damped sinusoids with characteristic frequencies and decay times that depend only on the mass and spin of the black hole. The typical frequency for a 10 solar mass black hole is 1200 hertz. But if it is spinning, if it is not spinning, but if it is spinning, then it could be 2 kilohertz. So the spin of the black hole and the mass of the black hole determine what the frequencies are, but they also determine how quickly it is going to die.
Satya, we had a small break from your voice. Can you repeat the slide 15 once again, please? Thanks.
Okay. Sorry. The key to understanding if the objects that we are seeing are black holes or some other kind of exotic object, test a fundamental theorem of black holes, namely that any deformed black holes, will come to as to how you can deform a black hole, then they emit their deformation in the form of space-time ripples. Black holes are warpage of space-time, and deformed black holes emit ripples of space-time itself. But these ripples, or frequencies of these ripples, more correctly, depend only on the mass and spin of the black hole. So moving on to next slide 16, I give you some example of what the characteristic frequencies are. For a 10 solar mass black hole, if it is non-spinning, it would be 1.2 kilohertz, whereas if it has a spin of 0.9, it would be 2 kilohertz. The mass and spin also determine how quickly these oscillations die. So a 10 solar mass black hole would, the quasi-normal modes, about half a millisecond. But if you have a 60 solar mass black hole, like the one that was detected by LIGO, they would last for something like 3 to 4 milliseconds. The effective number of cycles, which we call the Q factor of a black hole, is of order 2. So there are effectively 2 cycles, and that is the one that contains information about the quasi-normal modes property of black holes, and that's what we want to detect. So why do we want to detect these quasi-normal modes? Let's move on to slide 17. They are the true test of whether the final remnant of a merger signal is a black hole or some other object. If the final object is a black hole, we see a spectrum of modes, all of which depend on only the 2 parameters, the mass and spin. If it's not a black hole, then the oscillation frequencies could depend on parameters other than the remnant's mass and spin. And in fact, just the abrupt cutoff of the signal that you saw in the data is not quite enough to confidently claim that we are seeing a black hole. Requires to some degree that the signal respects the no-hair theorem. Moving on then, I gave you an example of just one quasi-normal mode frequency, but in reality, there are in an infinitely large number of modes. Not all of them are excited when a binary system coalesces or merges. But these modes are enumerated by 3 integers L, M, N, with L taking values from 2 to infinity, M from minus L to L, and N from 0 to infinity. And these are like spherical harmonics and overtones from spherical harmonics. More precisely, they are spheroidal harmonics, but I don't want to make these distinction here. So in general relativity, as I was saying before, the quasi-normal mode frequencies and damping times all depend on only the mass and spin of the remnant. And so if you measure one single mode, which means its frequency and damping time, we will be able to deduce what is the mass and spin of the object, assuming that it is a black hole. So if you measure 2 or more modes, then that would be a test of whether the object that we are observing is a black hole. If it is a black hole, then the parameters derived from different modes will all agree, otherwise they don't. And that's the basic point of testing the no-head theorem. Next slide shows you the different quasi-normal mode frequency, the spectrum of quasi-normal mode frequencies, omega, L, M, N. What is shown here is only n equal to 0 for different values of L. The frequencies keep on increasing. L equal to 2, 3, and 4 are shown here. For each value of L, as a function of spin, it also shows how these mode frequencies change for different values of M. When the spin is 0, just like in quantum mechanics, all these different modes are degenerate, but any non-zero spin to break that degeneracy. That's what you see here, the quasi-normal mode frequencies. On the next slide, you see the Q factors, that means the number of cycles. It is true that these are exponentially damped and lost for effectively only a couple of cycles. But that's only true when the spin is small. When spins are large and close to extremal, that is the maximum value possible, then you could have very long-lived quasi-normal modes. Fascinating to see such quasi-normal modes one day, very long-lived modes. But what did LIGO observe? What did we see? The next slide shows you the trace of the data. This is just a repetition of the curve that you saw. Some trace. From this, can we conclusively say we have seen quasi-normal modes? We need to do some analysis. We need to identify when the quasi-normal modes begin. On slide 22, I show you the reconstructed template corresponding to the data. So this is this shows the posterior distribution of the waveforms on the top panel, the strain as a function of time. The bottom curve shows you the evolution of the frequency. What you see here is that the frequency is increasing in time, and it reaches a certain constant value after the two objects have merged. And that corresponds to a peak in the amplitude of the waveform in the top trace or the top panel. And there, at that point, the frequency of gravitational waves has still not, it is still increasing. That's the point when the common horizon of the two two black holes have already formed. This is assuming that they are black holes. This is the model that is used in order to make these plots. And about a few milliseconds after, in this particular case, after that peak amplitude is reached, the frequency levels off. That is when we say we have reached the linear regime of the quasi-normal modes. And this is the ringing of the horizon. So the next slide shows you what signal to noise ratio we measure. So this is slide 23. Starting from the quasi-normal mode point, we measure a signal to noise ratio of 7.5. I should pause at this point and mention that this work, which Vishu worked on, right, for 40 years ago, continues to happen in Bengaluru because ICTS had a lot to do with this analysis, especially in assessing whether or not the seeing is consistent with that of a black hole. So moving on to the next slide, what next? What can we do with these ring-down signals? One of the fascinating things that comes out of a detailed analysis is not only do the black hole ring-downs contain information in black hole, the final black hole, but in reality, those ring-down signals also contain information about the binary from which it is formed, or the supernova from which it is formed, or the neutron star binaries from which it formed. And that is because we have so far only talked about quasi-normal mode frequencies and damping times, and we have not talked about the amplitudes of the signal. In the next slide, I show how quasi-normal modes would look in the space-based LISA detector. If you have a pair of 500,000 solar mass black holes colliding in the LISA detector, then one would observe not just a single peak corresponding to the dominant mode, but also higher order modes, and those are the two peaks. But depending on what are the masses and mass combinations, mass ratios, you could excite higher and higher modes. In the next slide, where I show on slide 26, that you really see a spectrum of different modes excited when a binary of different mass ratios and spins coalesces. It's like a black hole rainbow. This was one of the PhD projects of a student of mine who showed that the modes that are excited in the final remnant depend on the properties of the black hole. And by analyzing this, we should be able to learn what the progenitor parameters are. Next slide makes, namely the progenitor binary parameters just from the ring-down signals. I will avoid giving you all the technical details, but basically on the next slide, I show you how the property of the black hole can be determined from just analyzing the quasi-normal mode signals. That is, we don't see the binary itself, but only the remnant and how it is settling down. And from that, we can conclude what was the total mass of the binary black hole on slide 28. On slide 29, we show that we can measure the ratio of the masses of the two binaries, the two masses in the binary. And on slide 30 and 31, I show how the effective spin of the system, as well as a component spin on slide 31, how they can be determined as well. So quasi-normal modes are really very fascinating in that sense. They not only tell you about the black hole itself, but also how that black hole formed. Whether it formed from a binary or it formed from a supernova, and what the properties are. So what are the opportunities for testing these things? These are just theoretical studies. My next slide shows the upcoming gravitational wave detectors. And I just want to highlight that there's a network of detectors coming along, mostly in the northern sphere, with LIGO India, which helps to break some of the degeneracies that exist in the ones that are really in the northern part, whereas the LIGO India is closer to equator and breaks some of the degeneracies. So that's going to happen over the next 5 to 8 years. But we are planning already to go beyond that. So next slide shows an artist's conception of an underground third generation detector called Einstein telescope. That's the main graphic that you see, but would be first to improve the sensitivity of advanced LIGO by a factor of 3. That's a program that has been given the name Voyager. Beyond that, we hope to have this Einstein telescope, which is a total 30-kilometer arm length underground cryogenic detector, which will survey a volume times larger than the advanced detectors, whereas Cosmic Explorer, which will be another factor of 30 in volume, will be a 40-kilometer arm length detector currently being discussed in the US. In addition to the space-based program, the next slide shows you artist's impression of the laser interferometer space antenna. It's an L-class European Space Agency mission. It was selected for launch. The theme was selected for launch in 2034, but currently a proposal has been made to ESA, a very specific project. There's only one proposal, and we hope that it will be selected for launch. So what can these detectors do? The next slide shows you the signal to noise ratios that we expect in the future detectors. If you look at the first discovery, the total signal to noise ratio was about 25, and the quasi-normal mode, it was only a glimpse of the quasi-normal mode spectrum. We confidently detected only one mode with a signal to noise ratio of about 7. At the moment, that is not good enough to see the other modes. But moving forward, when LIGO detectors and Virgo detectors reach design sensitivity, will reach about 20, and increasing to 80 with LIGO India, if LIGO India adapts not just the advanced LIGO design, but a slightly better configuration, a factor of 3 to 4 better. On the time scale of 2030, Einstein telescope should see quasi-normal modes with signal to noise ratio of 200. But it is really when we have these third generation detectors like Einstein telescope, Cosmic Explorer, and LISA that we can see these quasi-normal modes with exquisite precision and test the true black hole nature of the objects that we are detecting. With that, let me conclude by saying that we are now developing an outreach program that is based on, this is the last slide, slide 36. We call it Black Hole Keyboard. It's a musical keyboard based on quasi-normal modes. It is, of course, digitally designed, and each key corresponds to a black hole of a specific mass and spin. And one of my colleagues here in Penn State in the music department is currently busy composing music with this new digital keyboard. So we have come a long way. It has been an honor to be a colleague, academic colleague and a friend of Vishu, but more than anything else, Vishu greatly inspired my own life, but lives of many, many people who he probably did not even talk to, but his books, his lectures were enough to inspire us. With that, thank you very much, and let me take any questions you may have. Thank you.
Thank you, Satya, for that wonderful talk.
Can you please turn the camera towards the audience, if possible?
Okay, just 1 second.
So, Satya, this is Ajit. I have a rather technical question again. So for this estimation of the binary parameters from the quasi-normal modes, the result that you have shown, what kind of signal-noise ratio is required to do this estimation?
Yeah, the ones that I showed you require something like, sorry, there was something going on with the video. Okay. I'm not able to see you, but it doesn't matter. We need signal-to-noise ratios of order hundreds. So it is not going to be possible with the kind of signals we are going to be detecting with the current generation of detectors. I think we'll have to probably wait until at least advanced LIGO plus.
Okay, so if there are no further questions, let's thank Satya again.